We've been introduced to series and we've talked a little bit about telescoping series. So I want to talk a little bit about another type. It's called a geometric series. And so the idea of a geometric series is that you have some number and you keep multiplying it by some ratio. So if you think about the idea of like similar triangles or some sort of similar shapes, if you multiply it by a ratio, it's either going to scale smaller or it's going to scale larger at each step. And what we want to do is we want to say, okay, well, if I have like a square of this size, and then I add the area of a square of this size, and then one of this size, this size, this size, this size, and I keep adding those squares together, is this thing going to converge to a finite area, or is it going to blow out to infinity? And that's really the end of the day. That's the whole idea behind a geometric series. So what we do is we formalize this by saying, okay, I've got some sort of series notation, and I have some sort of scale value in front times my multiplier to the end. So I call it a multiplier. Sometimes it's called a radius. And that number is just what you multiply each time step, right? As n goes up, it goes, like 1, 2, 3, 4 power. So it's just multiplying over and over and over and over and over. Now, one thing I want to point out, and this is very important about a geometric series, is that geometric series start off at 0. So that's kind of weird, right? We've talked about the idea that the index starts at 1. We've only really talked about that. And it's also really weird because depending on some definitions, they'll tell you that the domain of a sequence is positive integers. Well, clearly 0 is not a positive integer. So that's a little bit busted. You should not take that for this, because you can even have indices that start at like -5. And there are reasons to do that. There's actually really good reasons to do that, but we're not going to talk about that right now. For a geometric series, the index starts at 0. So be careful to watch out for that, because that can trip you up every time. Now, one thing that's cool about the properties of series is that if you have this little scale value in front, you can actually pull it out of the series. And that's pretty understandable, because if you have a number that's multiplied by every term and you're just adding it all together, well, you just factor it out, right? That's the same thing you would do with normal addition. If you have a bunch of numbers in a row and they all have the same coefficient in front, you can factor out the coefficient. And that's what you're doing here. And the reason why that's important is because the theory of the convergence of geometric series really only looks at this. This is just an add-on for generalizing it. Now, one thing that's neat is that this series only converges. It actually, if and only if. If you know that R value is greater than -1 and less than +1, so the magnitude is less than 1, you know it converges, guaranteed. And then alternatively, if I told you I had a geometric series and I told you it converged, you would have bounds on what that R could be. That's the idea of the if and only if. So if that bound is less than 1, then this converts directly to that. That's super helpful, because a lot of times we've seen convergent series, but we haven't necessarily said, oh, well, it converges, but I don't know what the sum is. Who knows? Well, this tells you directly what the value of that sum is going to be. A simple example is just taking 1/2 to the power starting at 0. Now, what you're doing here, if this was n equals 1, this would sum up to 1. We looked at it in the previous example when we took the square and we cut it in half and half and half and half and half. And that is true, but because n starts at 0, the first term of this is a 1, and then the next term is a 1/2, and the next term is a third, and so on and so forth. And then in this particular case, a is equal to 1, because it's not present, but it's clear that a is equal to 1. So you have 1 over 1 minus a half. Well, that equals 1 over a half, which becomes 2. So that's a pretty simple example, but you'll find that most geometric series can be manipulated to that. Now, one thing I do want to point out, and this is a very, very common mistake, I want you to listen to me very closely, is that people will start with a one-based infinite series, and they'll try to apply the geometric series formula. The geometric series formula requires that you start your index at 0. There are alternative definitions that require the index at 1. So if you are viewing other videos, or if you're somehow looking at other literature, there are alternative ones. I guess while I'm here, I'll write that. The alternative definition would be that. And hopefully you can see that that's really the same thing. So this is a way to start it at one index. So but be aware that the general theory a lot of times starts at 0. This is helpful for a number of reasons, but we won't get into those. But let's say I did start off with 1 where it was indexed at 1, and I had 1/2 to the n minus 1. Well, if I looked at the first 4 terms, well, when n is 1, that's 0. So it's 1/2 to the 0, 1/2 to the first, 1/2 to the second, 1/2 to the third. Okay, so those are my terms in the 1 indexed array. But I don't like that because these numbers, they're offset, they're mismatched. They're close, but they're mismatched. So what I'm going to do is I'm going to define, instead of an n minus 1, I'm going to define a sequence that looks pretty close to this, but I want it where the indices match. Well, the only way to do that is to start the sequence at 0, so that you have B0, B1, B2, B3. But what you see is that these are still the same numbers. So A1 is B0, A2 is B1, A3 is B2, A4 is B3. So no matter what, you're still representing it equivalently. So we could say, okay, well, I could write this series, or I could write it like this. This is that Bn series. And since I have it like this, I can then plug it in there. So a lot of times that re-indexing is a very clever way to manipulate. And I'm not really going to make, that's not really something I usually make students do, but it's a tool to have in your kit. And if you do more mathematics that involve series as time goes on, you're going to need to know how to do this, because there are certain properties that you want to exploit to combine multiple series into a single series.